and thank you everyone for coming along to this next webinar series. And today we will be presenting on behalf of Project 5.4, which trying to work on meeting user needs for information about water futures. So when it comes to climate projection in Australia, I believe many of us will be familiar with the latest and most state-of-art climate change in Australia projection released by the CSIRO and the Bureau in 2015. But maybe many of us are not aware that there has been a very long history of this national projection. Almost like 30 years ago, CSIRO developed the first sort of product, which is very simple, just projecting temperature and rainfall using one brochure or one page of information. And then through 30 years sort of work, the CSIRO and the Bureau finally produced something that is very comprehensive, very easy to deliver to the user in a form of climate change in Australia portal. So when we developed the proposal of this project, we have a vision that we're thinking that our project is a first few steps toward meeting the user for national projection for hydroclimate metrics for Australia in a consistent manner of the climate change in Australia projection that we have already. But the problem is the information required by the user is usually on beyond information of the mean or average. And then the range of projection are larger when we talk about hydroclimate projection, because we are not only including the information from global climate model, but also including from another type of model, which is hydrological model, downscaling, bias correction, etc. So how to interpret and communicate this sort of thing is a problem that we face. And lastly, there is some limitation, of course, in modeling science to meet all the user needs. So having these problems, we identified 3 objectives for this project. And on this talk, we will describe one by one of these objectives. So let me start by talking about the first highlight, which is trying to improve understanding of user needs, because that is very important before we are moving to the next step. So we do this by, but before that, I explain what we mean by hydroclimate metrics. So hydroclimate metrics are quantitative indices that are intended to capture some feature of a hydrological system. So when calculated over multiple years, they can track emerging properties or trends. So they are useful for monitoring and operational purposes. So in terms of improving understanding of user needs, we do this by conducting extensive literature review and double checking with the stakeholders, with the water sectors for some selected entities in Australia. And we learned that there are actually hundreds of hydroclimate metrics relevant to water resource management and planning in the context of climate change. So we're trying to map them into 7 categories. The first one is timing, which is a metric that indicating the starting or the end of a process. For example, when the maximum or the minimum runoff occur in a particular season, for example. The next one is magnitude. And this matrix is most of us very familiar. For example, the amount of runoff that we get, things like that. And then the third one is extreme variability. duration, state of water, as well as surface performance. And for the detailed information, you can have a look on a journal paper that written below this slide. So after we understand the user needs, then we develop framework for national projection for surface water metrics. And then by the end of the project, we develop that framework for a number of metrics. For example, on the category of magnitude, we develop the projection for mean runoff, the low and high flows. The coverage is for national. For extremes, we're looking at, for example, the lowest 7-day flow in 10 years, which is important for ecological purpose. Again, this is for national coverage. We also develop the drought, duration, frequency, intensity, and so on for national and NRM regions. We also looking at the surface and performance, which is more localized rather than national based, because we do this together with the stakeholder. And all the next speakers will talk about this in detail. But before that, I just would like to touch briefly for the benefit of attendees who are not very familiar with the projection information. So basically, usually projection were based on many global climate models or many hydrological models. So in this case, it is sometimes that some models may project an increase, others a decrease, while others may be showing no change. So to do that, we put the projection in a form of something that hopefully people understand. To do that, I just show you the analogy of house prices. So if you're looking at house prices around your neighborhood, you may see the median is 300,000, but it can range from as low as 150 to 400 to 25,000. So there is a range in the house prices. And in a similar way, the hydroclimate projection is showing like that. So we usually showing the median of the multimodal. For example, it shows increase in 10%, but the range of the projection could be from minus 20% to plus 15%. So that is what some of the picture that you will be seeing in the next few slides. So usually we show projection in terms of the median, like the map in the middle there, and then the lowest, the 10th percentile on the left, and the highest one on the right. So I hope this gives you a bit of idea about the maps that we will be showing. So now we are up to the first highlight, which is on runoff projection. And I would like to invite my colleague Hongxing Zheng to present this talk.
Yeah, thanks, Dewi. So this slide shows the components in modeling climate change impact on water. So it starts with the different greenhouse gas emission scenarios. This is followed by climate projections from global climate models in response to the emission scenarios. The spatial resolution in the global climate models are coarse, which within the downscaled to the catchment scale. The downscaled climate variables, in particular rainfall, was then bias calculated for input into hydrological models. There are uncertainties in each of the components, and they can be compounded through the modeling process, and we explored all this in the ESCC project. To meet users' needs, we show here projections that are consistent with CSIRO's climate change projection for the natural resources management region developed by Bureau of Meteorology and by CSIRO. The NRM climate projections also present changes to different rainfall characteristics, like mean annual rainfall, maximum daily rainfall, and daily rainfall with 20-year return period, as shown here. In our water projections, we assess previous please. In our water resources, projections, we assess how changes in climate, particularly rainfall, will translate to changes in stream flow, focusing on key stream flow metrics used in water resources management. Next, please. So this slide summarizes the approach used in our projection. The projection was developed for several emission scenarios, including RCP 4.5 and RCP 8.5, centered around 2060. We used the climate change signal from all 42 GCMs available in CME5, which is consistent with the NRM climate projections, to reflect the uncertainties caused by hydrological model structure. Several hydrological models like GR4J, Xinhai, Xiangjiang models were used. The hydrological models were calibrated against observed stream flow in more than 700 catchments across Australia. All the modeling was done with daily hydroclimate series, from which the different metrics can be relatively easily retrieved. So next. So back to previous. So we explore the following research questions, like how to better parameterize models for the different hydrological metrics. What is the impact of bias collection of downscale rainfall on the hydrological projection? What is the effect of hydrological low stationarity on the projection? And how to exploit hydrological models to simulate hydrological processes under climate conditions that have not been seen in the history. Next, please. So this plot shows the project changes in mean annual rainfall, mean annual potential evapotranspiration, and mean annual runoff across Australia. In this case here, for the high emission scenarios centered around 2060, equivalent to about 2 degrees of average global warming. The plot showed rainfall decline in northeast Australia and across southern Australia. This rainfall decline is amplified in the runoff decline, particularly in southwestern Australia and in the Murray River Basin and Victoria. However, there is considerable uncertainty in range in the future projection, and this range is also shown here. The take-home message here is a likely decline in rainfall amplified in the runoff decline in southern Australia, and management and the water and related factors need to consider responses to the range of plausible changes. Also evident is the increase in potential evapotranspiration, the middle column, demand, driven by the increase in the temperature. This will enhance the gap between supply and demand in southern Australia, further compounding the water management challenge. Next. This slide shows an example of interpreting the natural hydroclimate variability in climate change, using Southeast Australia as an example. We know that there is high natural variability in rainfall and runoff, whether runoff in a wet year can be 10 or 20 times higher than runoff in a dry year. Also evident here is the considerably less runoff in Southeast Australia in recent decades. The wedge shows the projections and average conditions into the future. In summary, the future will be hotter with higher evapotranspiration demand. Future rainfall is likely to decline, particularly the cool season rainfall. The decline in rainfall will be amplified in the percentage decline in runoff. Runoff variability will remain high, with wet and dry years on the background of a drying trend. Naturally, management is about managing beyond the averages. As Dewi mentioned, in this ESCC project, we review the literature and surveyed stakeholders to determine the key hydrological metrics used in water management. We assess the potential impact on these hydrological metrics And we share some of this in the next couple of slides. Yeah, and these are the definition of the matrix. And this slide here shows the projected changes for the different runoff percentiles from the low flows to the high flows. The changes in the runoff percentiles generally follow the pattern of rainfall and runoff projection. That is, the warmer and drier climate in the future, particularly in the southern Australia, will result in more frequent and severe drought, low multi-year storage reliability, reduced high flow overbank discharge, and floodplain inundation. Next. In terms of flow duration and environmental flow, this slide shows that the high flow days will decrease while low flow days will increase. And the minimum environmental flow indicated by 7Q10 will decrease, especially in the western and southern Australia. So water resources management will need to take into account and are taking into account the climate change impact on long-term water availability in all the hydrological metrics. How climate change impact can be considered in water resources planning will depend on particular applications. Steve's talk later will present an example. That's from me. Over to you, Dewi.
Okay, thank you, Hongxing. And now we talk about the drought projection, and I will be presenting on that matter. But before that, I just would like to say that drought can be defined in many ways, and there are a lot of indicators exist, and no single agreed definition on that. But typically, drought definition or indicators can be grouped into three types. The first one is meteorological drought, which usually based on the meteorological variable like rainfall, temperature. And the second one is agricultural drought, which is usually representing by soil moisture. And the next one is hydrological drought, which is represented by stream flow or flow into the lakes or ponds or things like that. And then the last one is what we call the economical drought or environmental drought. And for the last type of drought, it is affected by other things, not just climate. So what I'm trying to say here is developing drought projection can be tricky because there are many ways to do that. So in the latest NRM projection, the drought projection was only based on rainfall index, in this case called SPI. So through this project, we updated the projection so that it covers two indices and then cover 4 categories of drought and then looking at the 5 metrics of drought. So there are a lot of metrics to do that. So just to give you a flavor of the projection that we have, this is a map showing the projection for drought duration for rainfall index. As you can see, the median suggesting that most of Australia will experience increase in drought duration, but there are also on the lower side area that decrease in drought. So longer duration and more intense drought, especially on the southwestern Australia and the South Australia. When you look at the soil moisture index, larger changes is expected in soil moisture index rather than in the rainfall drought index. This is the presentation of looking at the median and the range of projected change. But we can also looking at a different way on presenting the projection by looking at the how many percentage of model agree with the projected change, because otherwise we will just see that the range of projection is large. So in this right map, I'll show you the percentage of models showing increase on projected drought duration. Brown meaning many models agree, and the one that has got stippling meaning more than 70% of models agree on the increase. So you can see there that if we are using only rainfall index, we will see just a pickpocket of Australia showing model high agreement. But if you're looking at soil moisture index, then you will got more area that showing much more agreement. In terms of correlation between projected rainfall and projected drought, I show here 3 examples from 3 models on the projected change in annual rainfall and the correspondent of the drought duration. So you can see that projected rainfall drought metrics actually reflect those in rainfall, but larger in magnitude. So when I look at this for all the drought metrics, the correlation between projected rainfall and projected drought are mostly negative, meaning if you get decrease in rainfall, drought will increase. But that is not the case for the frequency in drought. So the key message here is that common assumption that less rainfall equal to more frequent drought is not always valid, because it could be the other way around depending on the model. Also, it's not shown in this slide, but projected in soil moisture reflect those in rainfall, and potential evaporation has moderating role in projected soil moisture. Potential evaporation is where the temperature can influence the drought projection, and that's why we are looking at that. The other thing that we do as part of this project is also doing the model evaluation on drought, because initially there is no study on Australia. So in this case, I'm showing you a couple of models. The top model is the one that overestimate percent time in drought, and then the bottom one is underestimate. So if I put them in like a graphic, the top one is overestimate, the bottom one underestimate. And we can do this for all the drought metrics. So if it is go to the left, it means underestimate, like this one. And as you can see, the model tend to be overestimate on the frequency, but underestimate on other metrics. And no clear between better or worse performing models to create subset projection. So in drought projection, we use all of the model available because of that. And also we found that rainfall scale is not always a good indicator of drought scale. So we recommend that in the future, if one would like to develop drought projection, one need to do evaluation on the drought as well as ENSO, which we have not shown here, not necessarily just rainfall scale. So that is the end of framework for water projection. Now I would like to moving toward the third objective of this project, which is working together with users to demonstrate development and application of projection. And we've been working together with 2 users. First one is with the Murray-Darling Basin Authority. Second one is with the Western Australia Department of Water and Environmental Regulation. And for today, we present the second one, and Steve Charles will be presenting on that matter. So over to you, Steve.
Thanks, Dewi. I'm joining you from Perth, the Whadjuk region of the Noongar Nation, and I pay my respects to the traditional custodians of this land, to elders past, present and emerging, acknowledging that this is stolen land, never ceded. And I'd also like to acknowledge my co-authors on this project, in CSIRO, my colleagues Vanessa, Gurbin and Dewi. Vanessa and Gurbin particularly did a lot of the number crunching in this project, and Catherine from the Department of Water and Environmental Regulation ran the farm dam models that I'll show results from, so that collaboration is gratefully acknowledged. So yes, so we've been, it's a relatively small case study, but it's been coming out of a longer engagement. In fact, in southwest WA, there's been concerns over declining rainfall and research funding for that area since the mid to late 90s with the IOC projects. But with the ESCC Hub taking up some interest in the area, we ran a workshop in 2017 where we got all state agencies, but there was particular interest from the water agricultural sectors, and there's a report available on that. And we have produced one fact sheet on understanding climate change impacts on water resource management, as you see there, a general overview of our approaches, and then there's this bottom-up case study I present today. We're producing a more detailed fact sheet that will come out soon. So next slide, thanks. So this is our case study region. It's down in the Margaret River region of southwest WA, and it's a catchment of 90 kilometres squared, so not a huge area, but 55 of the dams in that catchment are used to supply irrigation to predominantly vineyards for growing grapes to produce our lovely Margaret River reds and whites. As you can see, so the map in the middle is the GIS showing the dams on the stream networks. On the right is a schematic from the e-water source modelling platform that the department used. So the Department of Water run models of the system under various scenarios, and climate change is obviously one of the things they're assessing in that respect. Next slide, please. When they're assessing basically risk to water supply and issues in the catchment, they look at individual dams, how reliable the supply is to those dams. So there's classify as high, medium, or low risk depending on how often they fill, how many years out of the record of 30 years that they look at, and also overall the catchment reliability, the proportion of dams filling at the high reliability. The catchment's also important not just for producing wine, but for producing water for the biota. So there are environmental thresholds for low flows to keep the system, water in the system, and also for high flows that has an important environmental need. Next slide, please. So what we did in this case study, which was right over the last year, we wanted to assess, well, the department have done a lot of work on climate change in WA in general, and specifically in Southwest with the drying climate. They've done a lot of case studies, and we've been involved, CSIRO has been involved in many of them. This was sort of a bit of a new approach because they'd already had their standard type scaling approaches to assess under different scenarios how their system might be impacted by climate change. In this case, we took a dry scenario from one of the climate change in Australia available application-ready data sets. So one particular GCM for one RCP, just sort of near-term future 2030. That GCM basically is about a 12% decline in rainfall from the 81 to 2010 baseline that we used. And we fitted a stochastic weather generator to that time series. Well, so we fitted to the historical observed silo data and also to the future data, scaled observed data, and we generated 1,000 simulations for current climate and 2030 climate. From those 1,000 scenarios, we selected a smaller number to run through the source e-water source farm dam model, predominantly for pragmatic reasons because there's a lot of manual handling. The model actually has an offline crop yield model, so there's taking data sets in and out of different models. It's not just plug and play. So we chose different scenarios for mean rainfall, so the 10th and 50th, 9th and 90th percentile mean rainfall, and also for 3-year minimum rainfall, because we thought we know that runs of consecutive dry years do have an impact on the water supply of the system. So we had those scenarios as well. Just jumping into some results, cognizant that we're running short on time, so I'll go through this reasonably quickly. So you can see the top half of this table is when we're running observed climatology. So the top row itself is what we get from the observed data, and you can see the overall catchment reliability is 94.5%, and the reliability in the driest year, so the proportion of dams filling to 90% capacity, is 89.1% of dams. And you can see if you do a straightforward scaling approach using that GCM scaling factors from that GCM, you'll get the top row in the bottom half, and you'll get a drop from 94.5% overall catchment reliability to 76.4%, and the driest year reliability drops from 89.1 to 69.1. So obviously something of concern and something to plan for in the water resource management of the catchment. When we look at the scenarios, though, the scenarios from stochastic generation of plausible climate sequences for both observed and future, focusing on the future, you can see that we can actually drop quite considerably more. We can drop down to an overall catchment reliability of 61.8% if we take the scenario that had the 10th percentile of the 3-year minimum rainfall. And we can drop to 32.7% in terms of reliability of the driest year. So that's a snapshot of the results, and in the next few slides I'll show some graphic representation of that. So in the top you can see these individual points are for different years in the simulations, and so the different colours are the red cross is for the future runs and the blue for the historical runs, and you can see quite a differentiation in the population. So certainly a shift towards lower rainfall in the future, and the dam filling per year percentage and the dam volume dropping considerably. And you can see that around 800 millimetres to the left of that, to less than 800 millimetres, it seems to drop off quite considerably. Important for the performance of the system is the bottom two plots showing the percentage full in the driest year, so where the 55 irrigation dams fit in terms of their the percentage full. You can see in the historical period it's quite a reliable system. Most of the dams under all the scenarios are filling in 90% of the years. In the right, with the future scenarios running through, the very first bar plot is the future historical from scaling. So you can see that this system would be probably assessed as still quite reliable. But if you look at some of the other scenarios, you can see that depending on if you choose a scenario based on 3-year dry periods, or you can get very considerable number of the dams down to the below 60% reliable capacity in the driest year. So quite a significant shift in the population there. For those of you, sorry, I was going to make one quick point. For those of you with very keen eyes, you'll see that on the future scenarios, there's actually 7 bar plots rather than the 6 scenarios I mentioned. We actually added one more, that last scenario, which is because we saw that 800 millimetre threshold. We added a scenario with a large number of years less than 800 millimetres, and that is also one of the ones that's down the left-hand side in terms of performance. Okay, sorry, Dewi, next slide. Yes, the environmental flows. So trickle flow is required, of 1 megalitre a day is required to maintain pool water quality and permanence of the stream flow, so that the macroinvertebrates can actually survive through the dry periods. And the high flow is required so that fringing vegetation is inundated, and that's for water quality and also for the ecological functioning. And you can see there's a distinct shift in the future climate towards low, because of the lower rainfall, more days in the lower classes. In fact, you can see that there's some of the scenario years are actually down at 0 days for the high flow, and there's one with 0 days for low flow even, so a very extreme scenario. Just jumping to the conclusions now, cognizant of time. So what we've shown is, and this is, like I said, quite a quick preliminary to some extent, but hopefully ongoing example of how we can do this work. The simple scaling itself therefore can underestimate the risk to water supply and environmental flows. We've showed that the system is sensitive to the variability as well as the mean change, so the 3-year dry periods, and so those issues should be taken into account. We ran 13 or 14 or so scenarios selected from a much larger range of stochastic simulations that we produced. We would have liked to have been able to run them all through the model and then sort of done a bottom-up mapping approach where you map the projection space back onto the performance across all those simulations. We weren't able to do that with constraints of computer modelling time and capacity in this project, but in the future we hope to do more in this space, and we're continuing to work through the whole project. There's been very strong engagement with the Department of Water and Environmental Regulation, and WA is developing its climate policy as we speak. Well, it's released at the end of last year, so it's starting to put that onto the ground now in terms of policy initiatives. So we'll continue to engage through the future hubs in this area. Thank you.
Thank you, Steve. So now we can almost finish with our presentation, but we would like to finish it with a bit of sharing on project reflection in the context of our initial sort of idea when we started this project a few years ago, which is we see ourselves just a few steps toward meeting the user needs for information on hydroclimate metrics for Australia in a similar way like with the climate change projection for Australia. So on surface water metrics relevant to users, we learned that there are hundreds of metrics to meet for, but it would be impossible if we meet them all. So we suggest to do stage approaches. For this, we start with mapping the priorities and commonalities, and we starting from there. And it is not always about the mean condition, the need of the user. And when we do this together with the user, we will know better what is needed. On modeling, projection range will remain large. So we suggest that in the future, we will do combining the top-down approach, which is involving the methodology that Hongxing explained, and the bottom-up approach that Steve Charles just presented to us. And there are many products and methods available to develop hydroclimate metrics. So coordination is a key and important. And we wish to work together with next-gen climate projection so that the hydroclimate metrics projection will be consistent with the climate change projection for Australia. And in terms of how we improve application of the products, we see that likely to succeed if we were to working together with users, but we need to be cautious that this requires time. Just like what Steve showed, we started in 2017 for the engagement with the Western Australia Department, and then we continue to do that up until now, which is very great. And thanks for the in-kind from them. Users are keen to work with us because they would like to have their planning robust, comprehensive consideration of things, including new science, but they may have no funding as well. So we need to be mindful on that. And the last point is that robustness of the metrics will not be affected by climate projection input only, but it will also affected by the metric formulation. So the users need to be aware where they can use a certain projection for a certain metrics or not for another metric, something like that. So I think that is what our presentation today. So thank you all for your listening. And in particular, we would like to thank our colleague in CSIRO who are part of the project. We also thank our partner in Murray-Darling Basin Authority, as well as our partner in Western Australia Department of Water Environmental Regulation. And last but not least is the next ESCC Hub, which is funded by the Department of Agriculture, Water, Environment, as well as CSIRO, the Bureau, and the 5 universities, as you can see on the bottom slide here. Thank you.